So I will be talking about recent results we obtained in the Bose-Einstein condensate group about superfluid dynamics on a surface, and especially dealing with fast rotating systems. And so we are in the laboratory for laser physics in Université Paris Nord, and it's about 10 kilometers north of Paris in the suburbs. So in the lab right now, we have 5 cold atom experiments. So I will be mainly talking about the rubidium two-dimensional system that we produce in the lab, but we have also in the BEC group sodium one-dimensional Bose gas experiment that is going on, and we do also a little bit of theory or numerical simulation to support the experiments. And we have colleagues that are experts in optical lattices. So they trap atoms, chromium and strontium, to do mainly quantum magnetism studies in optical lattice. And there is one group dealing with metastable argon and doing atom interferometry and atom optics. So before starting, this is the outline of my talk. So I will introduce you to our experiment and how we produce a superfluid on a curved surface. So how we create this, what we call the bubble-shaped trap. And then I will discuss the physics of rotating superfluids on this surface. And I will specifically discuss the fast rotation regime. And my last part, that will be quite small with respect to the previous one, will deal with the effect of dimensional reduction on a curved surface, and I will show to you some unexpected effects that we have obtained in the lab. And finally, I will conclude. So before going into the subject, I would just like to set up the stage and say that I'm not an expert in helium superfluid physics, so I apologize in advance if I don't cite proper works related to this area. And I will also remind you that I will discuss superfluid properties of Bose cases in low dimensions, and as you probably know, this is connected to the Brzezinski-Kosalis-Tarles physics in 2 dimensions. So this is the mechanism that provides superfluidity in our system, but I won't discuss this physics today. And I want to also say that I will discuss trapped systems. So systems where there are significant finite size effects, and also Bose cases that are always weakly interacting. So if I compare the atomic density in atom per cubic meter to the scattering length, so the typical length scale of the two-body interaction, I always get this number that is rather small as compared to 1, so at least in our system. And so this defines a weakly interacting Bose gas. And yet we still have some system that is quite degenerate, as the phase space density, comparing now the atomic density to the thermal Tilbury wavelengths, is fairly large. And in my talk, I will show to you many pictures of our system that are real experimental density profile that we record either in situ, so we get the atomic distribution as a function of the space coordinate, or after a time of flight experiment, that is, we switch off the trap and let the gas expand, and in this way we record something that is close to the momentum distribution. And we compare this distribution either in situ or after time of flight to models, so usually the Gross-Pitevsky equation or some homogeneous system prediction that we connect to our trap system using local density approximation. And for example, here you can see that we can fit the density profile of our gas by a bimodal density model that allows us to measure the temperature of the system, for example. So about some numbers, so we trap quite a it's not very large atom numbers, and the temperature are in the nanokelvin range, typically lower than 100 nanokelvin. And the chemical potential that is the other important energy scale in our system is in general between 100 Hertz and 1 kilohertz. So these two energy scales are the one that we consider if we want to discuss how much we are in a low dimensional regime. And we compare these energy scales to the typical energy scale introduced by our trap. So just a few other introductory words about superfluidity. So in what we can do in atomic Bose systems, or what has been already done, is to study specific properties associated to superfluidity, as for example, the possibility to create a persistent current. So if you trap atoms in a circular atomic waveguide, so a trap that has the shape of a ring, you can induce circulation, a current, atomic flow in this system, and you can observe an atomic flow persisting for a very long time. So in analogy with persistent current in superconductivity, for example, then you can directly measure the existence of a critical velocity to create excitation in the superfluid. So there are many experiments having measured that feature, but I show two examples. So one example in the obtained in Paris in the group of Jean Dalibard, where they measured the increase of the temperature in a 2D atomic system, depending on the relative velocity between an obstacle and the gas. And they have seen that below a critical velocity, there is almost no heating, and there is a sharp increase when the relative velocity exceeds the speed of sound, basically, in the system. And this is a generic feature that can also be observed in other superfluids, as for example, more exotic superfluids like polaritons, where you can also see here directly the density profiles, the modulation induced by a flow, a supersonic flow around an obstacle. So depending on whether the flow is supersonic or not, you can see excitations or almost no excitation. And finally, as we will discuss rotation here, I just remind you that with these superfluid systems, we expect to see quantized vortices when the gas is rotating. And this is, for example, a picture taken in our lab where we see the more or less the abruptness of a vortex lattice that you expect in the ground state when the gas is rotating. And just a last word about a field that is, I think, increasing in our community is the fact that now we are really in the position of shaping the traps in which we trap atoms to realize now real analogs of mesoscopic devices that are used in the mesoscopic physics, as for example here the first realization of the analog of a squid with atoms in this publication. Okay, so in this talk I will be discussing superfluid rotation on a curved surface and some properties also at equilibrium on this curved surface. So this the experiment goes as follows. So we have a fairly standard setup with a two-stage atomic cooling first in a two-dimensional magneto-optical trap, then we transfer the atom to a three-dimensional magneto-optical trap. And the originality of our setup is that when the atoms are sufficiently cool, we load them in a magnetic trap, and this magnetic trap is obtained by a pair of quadrupole coils that are attached to a moving translation stage. So we move the quadrupole trap to a tiny glass cell that you can just see here in the experiment, and we transfer the atoms in another magnetic trap, still a quadrupole trap, And we do the experiments here far away from the 3D mode. And this allows us to have a very good vacuum here and lifetime in the trap up to 2 minutes. So that would be, as you will see, important to create the fast rotating gases. So for technical details, we need additional light, so green light, to create our condensate. And then we transfer the atoms in a bubble-shaped trap. And we typically observe, after time of flight, very anisotropic profile, confirming the fact that we have now squeezed the system. So we see that the gas expands faster in the vertical direction than in the horizontal direction. And this means that the trap energy is larger in the vertical direction. So how do we create this bubble trap? We use a technique that is called RF dressing, and that allows us to realize adiabatic potentials for the atoms. So the idea is to confine the atom to an isomagnetic surface of a static magnetic field, and in our case, it's a quadrupole field. And as I will show in a few moments, we can have the atomic spin following a local eigenstate of the system, and this results in a strong confinement to the surface. And also we can get very smooth and tunable surface potential in that way, so that's interesting for our studies. And if you are interested in this topic, there is two recent reviews by Barry Garraway and Hélène Perrin on this kind of experiments. And I must also say that there are, at least in the group of Chris Foote in Oxford, there are other experts of adiabatic potentials for ultra-cold atoms. So the idea is the following. If you take an atom, so for our case, it's rubidium-87, it's in its electronic ground state, so with total spin F equal to 1, and you put this atom in a magnetic, inhomogeneous magnetic field, you will have several states that have different energies due to the Zeeman effect. And if you now couple the different Zeeman states with radio frequency photons, you know probably from quantum mechanics that it's better to look at this problem in the trace state basis, meaning that you subtract the energy of one photon from the m equal 1 state, and you add the energy of one photon to the m equal -1 state to evidence that you have level crossing at some point. And due to the RF coupling, you know also that you will have some avoided crossing between those states. And that's exactly what we obtain if we diagonalize the Hamiltonian in the using the correct approximation. So usually rotating wave approximation, we find that the potential has a well-defined local minimum at a given position in space that is given by the resonance condition between the radio frequency energy and the Zeeman substate energy difference between the different states. So this usually results in a very simple formula to describe the potential. That is, the potential depends only on the local detuning between the radio frequency energy and the bare Zeeman state, and also depend on the radio frequency coupling, so the strength of coupling between the states. That will depend also on space, because the magnetic field orientation is not the same with respect to the radio frequency polarization that we shine onto the atoms. So now if we look at this potential, we can repeat the same procedure and add another extra radio frequency photon, coupling now directly the dressed state. And this can be useful, for example, to control the trap depth, so to define a maximum energy at which we will expel the atoms. And this allows us to set the temperature in our system. Okay, so if we now look at the three-dimensional potential, so a cut in the three-dimensional space, and here, because of the choice of our geometry, the potential is invariant by rotation around the z-axis. So we see that the potential results in a ellipsoid shape where the local energy minimum is on this eggshell shape. And because of gravity, we have an extra term in the potential that makes all the atoms accumulate at the bottom of this surface. And now if we focus on the global equilibrium position, we get a vertical confinement that is mainly defined by the avoided crossing here between the magnetic states that can be fairly large, of the order of a few kilohertz, while the typical frequency of oscillation on the surface are set by the pendulum of the atoms moving onto the surface, and it's typically frequencies that are in the range of tens of hertz. So we get a very flat trap, a trap that is fully controlled by the polarization of the radio frequency. So we can choose to make a cylindrically symmetric trap, making omega x equal to omega y, or to make an anisotropic trap. And for example, here we have a picture in situ from the top view of the system with a slightly anisotropic cloud, while the time of flight expansion shows us how different are the trapping frequency in the vertical and the horizontal direction. And we have used this trap to study, for example, two-dimensional dynamics of a condensate in this system. And for example, we have evidenced the collective modes that can occur in the dynamics, so the oscillation modes and the compression and scissors modes in the system. So now I would like to discuss how we make this particular trap rotate and how we achieve fast rotation. So first, why do we want to do fast rotation? It's mainly because there is this formal analogy between the Hamiltonian of ideal two-dimensional rotating atomic gas that is analog to the Hamiltonian of a 2D electron gas in a uniform magnetic field. And this is interesting because we know that this is related to quantum Hall physics, and we have the hope to be able to simulate quantum Hall effect with atoms. So to see this analogy, it's very easy. You take the Hamiltonian of the two-dimensional harmonic oscillator and you look at the eigenstates, and you see that there is this structure of energy levels where manifolds of degenerate levels are different because of their angular momentum. And now, if you introduce rotation, you will lift the degeneracy between the different angular momentum states. And if you manage to match exactly the rotation frequency with the trap frequency, you get infinitely degenerate, in principle, level structure that is, in fact, the Landau level structure from quantum Hall effect. And in particular, the fact that you have a highly degenerate ground state here is particularly interesting when you turn on the interaction between the particle. And so this has been extensively discussed in the literature, and there are very recent results at MIT in the group of Martin Swerlein that have prepared some state in the lowest Landau level and studied its dynamics. And I would like just to mention that there is another approach to realize this system and simulate this physics with atoms using artificial magnetic gauge fields. So the idea is now to trap atoms in optical lattices and simulate the effective magnetic field with laser coupling between the atoms. And there have been also recent progress in that direction over the past few years. So in our experiment, we use our control over the trap geometry to induce a slight anisotropy in the in-plane frequency. So we start from symmetric trap where both frequencies are equal, and we just introduce a small anisotropy between the X and Y axis, and we can choose also the direction at which this anisotropy is located. And in the new basis, we obtain this potential, and we can control again by the radio frequency polarization. By controlling the radio frequency polarization, we can control the time, the angle theta here, and we can make it rotate at some frequency. And it is known that if you do that, so what you excite is a particular deformation of a condensate, and it will couple to a specific collective mode that is the M=2 quadrupole mode. And there is a resonant coupling for some steering frequency that is about 24 Hertz in our system. So when we do that and we measure the density after a time of flight, we see that we manage to create a vortex lattice. And if we increase progressively the rotation frequency, we see that the gas expands, gets larger, and the vortex lattice contains more and more vortices until we have difficulty to see the vortex lattice. So here we can still see individual vortices, but the triangular lattice is not well defined. And we can reach even situation where it's very hard to see whether or not there are still vortices in the system. So we suspect that we see here some melting of the vortex lattice with the increasing rotation frequency. And this we can compare to previous experiments, again in the group of Jean Dalibard in Paris, where similar behavior was observed. But the main difference here is that we start with a system that is very confined in the perpendicular direction, perpendicular to the plane of the image. So we have almost point-like vortices. Whether in this experiment, it was a three-dimensional cigar-shaped BEC, so the vortex are very long in the plane perpendicular to the imaging axis. And in that case, we expect different mechanism for the breaking of the vortex lattice. So you can have excitation of the vortex lines in this situation, and we don't have those in our almost 2D system. So currently we are still working on determining whether it's truly or not a melting of the vortex lattice and associated to possible phase fluctuation in 2D. So this is still work in progress. What we have measured is that we are well into the diffuse vorticity regime, meaning that we have enough vortices everywhere to have effective solid body rotation at large scales in the system. And we tried, starting from this last picture, to increase a little bit more the rotation frequency to reach our trap frequency, that is 34 Hertz. So we are still below the trap frequency here. And then we have a problem that is well known in harmonic trap, is that if we rotate too fast, we start to cancel completely the harmonic trap. And so this can be seen in the effective potential in the rotating frame. If you include, for a harmonic trap, if you include the effect of the centrifugal force, then you get a potential that will completely vanish at the trap if you rotate exactly at the harmonic trap frequency. And the solution to that problem, so this is experimentally, this is a problem because then the atoms are not trapped anymore and you lose them. And the solution to this problem is to add extra terms to the potential. And if you do that, then you can stabilize the potential. So here I have drawn a few curves for different rotation frequencies. And in particular, if the lambda quartic term is not 0, you can stabilize the system that is rotating exactly at the harmonic trap frequency. And even you can go beyond this rotation frequency and create some Mexican at effective potential in the rotating frame. And it turns out that our bubble trap has naturally higher order terms because the atoms are not in a harmonic potential, but they are constrained to move onto the surface. So there are these higher energy, higher order terms, and the possibility to reach new shapes of the potential with local minima at finite radius triggered some theoretical works that predicted that in that case, for this harmonic plus quartic trap, you expect to see a transition from a vortex lattice with some order to a system where you have a large hole in the middle and then something that is called a giant vortex where all the vorticity is now contained in the central hole. So these simulations were done for very small atom numbers at the time, and if we do the same simulations for our parameters with a large different trap and a large atom number, we get more transition like this. So from in principle Abrikosov vortex lattice to a central hole that can be fairly large, but still a system with so the atoms, we expect the atoms to form a ring, and inside this ring, we expect to see many vortices. And this is what we call the dynamical ring. So it's not a giant vortex, but it's something where there are still many vortices inside the bulk of the ring. So if we do the experiment, what we observe. So we start from a condensate at rest in the trap, and then we steer the anisotropy with a fairly large value of the deformation and at a frequency a little bit below the trap frequency. And if we do that, we create a strongly out of equilibrium system. And in fact, what happens is that we have a rotation frequency that is larger than one of the confinement frequency in the weak direction when the anisotropy is on, whereas it's still lower than the strongly confined direction, and it results in this very anisotropic cloud that is rotating. And after some time, the system relaxes to symmetric trap. So I must say that these are in situ images, so inside the trap. And we see that progressively there seems to be less and less atoms, and at the same time we start to see a depletion in the center. And this we understood because we have a RF knife during the whole experiment. So this RF knife sets the trap depth, so it limits the energy of the atoms. And it turns out that for our parameters, this RF knife also induces a selective evaporation mechanism, and it will favor the evaporation of atoms with low angular momentum. So in fact, atoms close to the trap center, to the axis, the origin of the trap, will have a higher probability to get evaporated than the atoms that are rotating on some orbit. And this, we can clearly see it if we lower the trap depth. So if we force the evaporation, we see that we lose atoms mostly at the center, and that the remaining atoms will have larger orbits, so higher angular momentum. So we increase the angular momentum by the evaporation. And this allows us to realize this quite dense. So this is the atomic density in atom per micrometer square. So typically 15 to 20 atoms per micrometer square with fast rotation and quite long lifetime, because you see we can see this rotation for over more than 1 minute in total. And a little bit later, I will describe a spectroscopy experiment where we again turn on the anisotropy, this time at a very small value at a different rotation frequency, and this will allow us to probe some collective mode of this rotating gas. So we observe a full depletion of the center, so something that is close to a giant vortex or a dynamical ring. And if we look at the radial profile of this gas, we see that we can compare it with a prediction for Thomas Fermi density profile. So the true Thomas Fermi theoretical density profile is the dashed line here. And if we take into account the finite optical resolution of our imaging system, we obtain a curve that is slightly blurred by the finite resolution, and that matches quite well our data that are the magenta circles. And in fact, what we can rule out clearly is a semi-classical model saying that if it were a gas at the critical temperature, so no condensate, no superfluid, but just a classical gas at the critical temperature, we expect that this profile would fill the trap up to the center, and that's ruled out by our experiment. So what makes this ring so special? If we let it expand from our trap, we can measure directly the rate of expansion, and we find that it follows quite nicely a ballistic expansion. And from this ballistic expansion, we can directly measure the rotation rate or the linear velocity around the ring. And we find that this velocity is of the order of 7 millimeters per second. And from the in situ density picture, we can record the atomic density, the local density. We find that it's typically this value, which gives us an estimate of the speed of sound of the order of less than 1 millimeter per second. And if you take the ratio of the two, you conclude that the gas is flowing at Mach 18, so 18, with a linear velocity 18 times above the speed of sound. There is a related experiment by the group of Wolf and Klitzing in Crete that did the same kind of fast rotation, but while holding the atoms in atomic waveguide. In contrast, in our experiment, the atoms are just moving on the surface of a bubble, but there is no waveguide maintaining this circular shape. This is just the balance between the trap and the centrifugal force. Okay, so how can we prove that this system is still superfluid? You can notice that I have not shown to you any vortices here, and that's because if we try to see, so we cannot see vortices in situ because they are too small. So usually what we do is we release the trap and we let the cloud expand, and this magnifies the core of the vortices and make it, and then we can image them on the camera. But the problem is that the system rotates so fast that if we take a picture after a time of flight at which we expect vortices, then we have a very poor signal to noise ratio on our vertical camera, and we cannot see vortices at all. So to probe for the superfluid or coherent properties of this object, we did quadrupole mode spectroscopy. So the idea, as I mentioned before, is to rotate a very small anisotropy for some time and then measure the consequence on the cloud ellipticity. And if we do that, we can, as a function of the rotation frequency, see resonances. In general, we see two resonances corresponding to the two quadrupole modes, omega +2 and omega -2. So these are the two m equal ±2 quadrupole modes. And you can see that there is here one resonance that is at a negative frequency and another resonance that is at a positive frequency. And here, positive or negative is with respect to the, so a positive frequency, positive excitation frequency means that we rotate the anisotropy in the same direction that the flow. And if it's counter-rotating, then it's a negative frequency. And so we observe these two resonances. You see that they are not at the same absolute value. That's because we do this spectroscopy on a system that is already rotating. And the prediction, so this is well known for a BC in a harmonic trap, for example, and you can predict even the value of the frequencies. It gets a little bit more complicated in a harmonic plus quartic trap as we have, but you can still do some theory and predict that these modes still exist. And indeed, we see this behavior in the experiment, whether if we probe at a non-resonant or resonant frequency, we observe a clear anisotropy in the dynamical ring that we have. And the main result from the theory is that the theory predicts that the omega -2 mode is always counter-rotating with respect to the flow. And what we see in the experiment when we do the spectroscopy is that for this particular mode, as the dynamical ring forms, we see a clear evidence of a shift of the resonant frequency to the positive frequency. So this is there is a very clear signature, and it happens approximately at the same time as the dynamical ring forms. So here before, for the blue curve, for example, the density depletion at the center of the trap is not complete. So there is it's a system in a harmonic plus quartic trap, but it's not yet a dynamical ring. And as we cross this line, it coincides with the formation of the dynamical ring. So this is something that we don't understand. It's not. It seems it's not due to an approximation of the theory. So, for example, some non-valid approximation, because we cannot reproduce it also from Gross-Pitevsky equation, Gross-Pitevsky simulation. So that's still something that we don't understand. So in the remaining few minutes, I would like just to discuss rapidly what we have seen about dimensional reduction on the surface. And so why do we want to look at this problem? Well, the idea is that if you have this curved surface, this eggshell trap, and you manage to fill it with a superfluid, then you will have interesting topological effects. So, for example, vortices must come by pairs, and these are has some consequences on, for example, Brzezinski-Kosaris-Towers physics on this surface. And this has triggered many recent theoretical works about studying superfluid properties on closed surface. And this is also triggered by the fact that there is now a BEC machine on the International Space Station. And one of the experiments that can be carried out on this BEC machine is the prospect of making a shell-shaped trap for a BEC and taking advantage of the low gravity environment on the ESS. You can imagine filling the whole shell with atoms. So as we have not microgravity environment in our trap, we still try to find a way to look at this physics in our experiment. And the idea is, can we fight gravity? And in fact, if you follow the atoms on the resonant surface, so where is the minimum of energy of the adiabatic states, you find that there is a very simple approximate expression for the potential. And in fact, for a choice of a sigma plus polarization, the Rabi coupling term has exactly what you need to compensate for gravity, meaning a term linear in Z with a minus sign. And if you choose carefully your parameters, so if you choose carefully the radius of your bubble, you can compensate gravity. And if you do the numerics, you find that indeed the isopotential is now filling the whole surface, the whole bubble. And so we try to, changing the bubble radius is a rather simple experiment. You just need, for example, to increase the magnetic field gradient of the quadrupole trap. So we tried that in the experiment. And what we have seen is that indeed you can have this way the atoms expand on the surface. And we did some Gross-Pitevsky simulation just to check that it was really happening as we as the gradient increases. So you see that we can more or less fill almost half an hemisphere of the bubble. But then as we continue increasing the gradient, we see that a new feature emerges. There is a ring that forms that seems quite robust. And this is surprising because even at this value of the gradient expressed in these units, we are not, in principle, we should not overcompensate gravity. So push the atoms to the top, for example, of the bubble. So that's a little bit unexpected. And what we have missed in the simple analysis I presented to you is the fact that our bubble, in our bubble, the potential is not separable at all. And then you have to take into account the transverse confinement. So the idea is that if the atoms are really localized onto the surface, then they are in the ground state of the transverse confinement. And we know from quantum mechanics that they have a 0-point energy associated to this harmonic oscillator ground state. And the problem is that the confinement is not the same everywhere on the bubble. And in fact, it increases as the atoms go to the top. So we have an extra term in the potential that is the 0-point energy of the inhomogeneous transverse confinement. And this provides a very effective barrier to repel the atom from the top of the bubble. So I won't go into all the details, but the main, maybe the main message of this slide is that we have a strong barrier effect due to a dimensional reduction. So we interpret it as a dimensional reduction effect. It's the 0-point energy of the transverse confinement that prevents the atom to fill completely the bubble and in particular localize them at a finite radius. So there are all other effects that you need to take into account to get agreement with the experiment, but that's the main effect. So with this, I will conclude. So I have presented to you some of our experiments on Bose gases in fast rotation. So I've started with the moderate rotation and the observation of vortex lattices. So I have not much discussed, but we think that we have indication of vortex lattice melting, and we are working on getting quantitative on that point. And the main result I've shown to you is the formation of a long-lived flow that is a supersonic flow, and that lasts for a long time in our trap. What we want to do now with this system is we would like to investigate the decay mechanism. So add an obstacle, maybe a moving obstacle in the system, and measure, for example, if we can see a critical velocity to excite to slow down the flow. And maybe a long-term goal or longer-term goal would be to realize a giant vortex. And for this, we need to increase more the rotation, and it's not an easy thing to do. And then I have shown to you how we were able to compensate gravity in our system, and how this resulted in a new ring trap where the ring shape emerges because the atoms are really confined by, really in the ground state of the transverse harmonic confinement. And this is something that we like a lot, because it's a kind of direct proof of the fact that the atoms are on the 2D surface. They localize because they are 2D. If they were not in a 2D state, if they were in some superposition of many excited states, they would occupy a much larger surface on the bubble. And now we are thinking of combining the ability to rotate the trap and to compensate the gravity to try to explore vortex physics on the curved surface. So what we can realize is half an hemisphere filled with a superfluid, and try now to see the effect of the curvature on the vortex physics on this surface. And before finishing, I would like to introduce you to the people behind the work. So the BEC group is led by Hélène Perrin in LPL, and this work was mainly done by Yang Guo and David Ray Yang defended his PhD thesis last year, and David is now the senior PhD on the experiment. And the last work I presented to you, the one about superfluid on a bubble surface, was an original idea of Vanderlei Bagnato that really pushed us to investigate this topic. And we did some of the experiments together with a PhD student of his group during one of his stay in our group. And with this, I thank you for your attention.
Right. Thank you very much for an excellent, engaging talk. I know I have a lot of questions, but I'll let, if anyone else has questions as well, please either pop them in the chat or raise your hand. But I'll just start with one of mine then. So many moons ago, when I was a graduate student, we did some work trying to look at vortex lattices in oblate BCs. So the vertical trap frequency would have been like 100 hertz instead of your kilohertz. And we found that we could never get the lattice to crystallize in that geometry. And so I'm wondering, is there any trick or long lifetime required, or is it just happens when you're spinning up a lattice in your trap?
So, so if I'm getting the question correctly, so the question is, what helps us to get the vortex lattice at high rotation frequency, right?
Yeah, what helps you to get to have the vortex lattice actually crystallize, given that you're working in a very strongly 2D system?
Okay, so I am not totally sure of the answer to that question. So currently we are looking at this question. So why can we see? So if I go back just here, why can we create vortex lattices up to some point, and then it seems much harder? So so what I must say is that those vortex lattices are typically, we see them like after 10 seconds of thermalization after the rotation. And probably the fact that our knife is helping to increase the rotation or favors atoms that are rotating is maybe a good thing. The fact that it helps maintaining the rotation. So I don't know what was also your system, but in our case, we also really finely tune the trap to have a very well rotationally invariant and very smooth trap with almost no defect, I would say.
Well, I'm guessing the traps that I was working with had some defects with them, so that's also a good point. But okay, I'm quite interested in this. So we've got a couple other hands raised. Samuli, do you want to unmute and ask your question?
Yes, thanks. Well, I understand this may be, let's say, wild speculation at this stage, but can one imagine a two-dimensional superfluid of some other topology than a sphere? And what might be the consequences?
Okay, so yes, you can imagine other topology. So at least theoretically, it's possible in the experiment. So it's in principle doable to achieve other surface shape by adding external other control fields. So for this, you need to realize what is known a time average adiabatic potential. So the idea is that you have this bubble trap, and then you start to shake it in some pattern. And when you do that, if you do it fast enough for the atomic motion to average, but slow enough so that the eigenstates remains well defined, then you can tune further the geometry, and you can realize other configurations. So I know that Chris Foote is working in that direction, and also Klaus von Klitzing. But then the difficulty is that as you add an extra time scale or energy scale, if you want, it gets very hard to have a well-defined hierarchy of strong confinement in one direction and weak confinement in other directions. So it's possible to tune the geometry of the surface, but then it makes it really hard to have a well-defined 2D system, because the localization of on the surface is becomes quite weak. So I don't know if I answered your question.
Yes, at least other parts of it definitely. Then we'll maybe I should talk to your theorist about what may be the consequences of having more complicated topologies. But yeah, thanks anyway.
Mm-hmm.
Davide, do you want to unmute and ask your question?
Yeah, thank you, Kelly. Thank you, Romain. It was really a nice talk. So I'm going to ask you a question regarding the observation of the Mach and the velocity. And I have to say that I missed part of your talk, so maybe you said that, and I'm sorry if you said it. But so you mentioned the conclusion that basically you reached Mach 18. So very naive question is that, but shouldn't any I don't know, perturbation or defect in your potential, I mean, create well, small enough able to destroy this Mach 18? Does it make sense what I'm saying?
Yeah, so that's a good point, and the answer is that maybe the short answer to your question is, in principle, it's true, but in fact, if you consider the coupling of one defect with a superfluid as a function of the relative velocity between the superfluid and the defect, you will get a maximum of coupling at the speed of sound, basically, and then it decays, and it decays quite fast. And it means that if you move a defect very fast with respect to the speed of sound in a superfluid, you don't expect many excitation, not because you are below the critical velocity, but mainly below because things happen too fast for the atoms to follow.
I see.
And so if you consider a superfluid that is moving very fast with a Mach 18 velocity, and then you put an obstacle, what will happen is that the kinetic you have to have a defect with a very large energy to overcome the kinetic energy of the background flow, and then you run into, I would say, other troubles, because if you have a very large defect, then it's hard to compare to the Landau's criterion that is for a weakly, very small defect affecting the system.
Right. Okay. So it's kind of counterintuitive. I mean, you would expect a cascade of defect happening, but
and so this has been seen in an experiment in the one-dimensional optical lattice by the Lens group.
Mm-hmm.
So it was some time ago, and they have seen, so they impart some velocity on the cloud, and they put a I think it was a cloud moving in a harmonic trap, and they superimposed a weak lattice, and they have seen that if the cloud is moving very fast, in fact, it doesn't see the lattice at all, and this does not dissipate the motion.
Okay, well, thank you, Romain.
All right, Aidan, would you like to ask your question?
Thanks, Kelly, and thanks for the really nice talk, Romain. I was wondering if you could use since you had sort of dynamic control of the shape of your bubble, whether you could use that for either 2D delta kick cooling or to collapse the sort of pancake wave into a Bessel wave or something like that.
So I'm not sure I see what you mean.
I'm just so when you turn the gravity off, you can do that in a kind of a controllable way. So you have, it's not, you could effectively change the but is it because of the radius? I thought that maybe you could control effectively the position of the atoms around the sphere. So basically by partially turning off the anti-gravity, effectively turning the gravity off and then turning it back on again briefly, you could freeze the cloud and make it cooler in 2 dimensions, or maybe even collapse the cloud and make a sort of a incoming wave which has that makes a Bessel wave, like some of the experiments that Malcolm was doing in Los Alamos.
So okay, so we have not thought about delta kick cooling, but definitely we have thought about like creating a ring trap at this position, for example, and then switching off the gravity compensation quite fast.
Okay, yeah.
And yes, to force the atom go back to the to the bottom of the bubble and see what happens during the collision, or symmetrically, not to push gently the atoms to this position, but rather quench the anti-gravity to see what happens. But we are thinking about it. We have not done anything yet in that direction.
Oh, there's always plenty to do. I also like the Mach 18 as well. I'm regretting that I didn't use that as a sales pitch for my 1.4 meter per second BEC and the big rings. It's a good one. So thanks.
All right, and then we've got a question from Grigory.
Can you hear me?
Yes.
I just want to comment about this Mach 18. I think there is no problem, but maybe it's not okay. So look, in rotating frame, vortices are at rest, normal component is also at rest, and that's why there is no any instability. So there is no problem. So you can have any Mach you want, but of course it should not destroy the cell. That's all.
So you're saying that the vortex lattice structure in the rotating frame is fixed?
It's fixed. It's at rest.
Yes, but
and that's why it's at rest with the normal component and at rest with the environment. And that's why there is no instability at all.
But then the question would be, if we, for example, if I add to this problem a static obstacle that would be at rest in the lab frame, then
if you add static, yes, that's of course.
Okay, so I think one of the previous question was, I mean, the question is, do we have defects or static defects in the trap? And we think we have very little defects, or the trap is very well controlled. And now we plan to add some defect and to see the effect. Yes, but you're right that in the rotating frame, everything is at I mean, the normal fluid and the superfluid are there is almost no relative velocity.
Okay, thanks.